Hey everyone, and welcome to this explainer. Today, we're diving into the absolute bedrock of computer science and discrete mathematics, set theory. If you've ever wondered how databases process those massive SQL queries, how search engines can instantly filter millions of results, or even how core data structures like hash sets actually work under the hood, well, you're in exactly the right place. Set theory is literally the master key to all of it. It's also the foundational prerequisite you have to master before you can even touch things like relations, functions, or mathematical induction later in your course. We're going to build your intuition right from the ground up so you can absolutely crush your university exams and write much better, more optimized code in the real world. Let's get into it.
Here is our roadmap for today. 1. Unit I course context. 2. Set fundamentals and types. 3. Core set operations. 4. Laws and Cartesian products. And finally, 5. Mixed practice problems.
Section 1. Unit I, Course Context.
Take a look at this syllabus. You'll notice set theory isn't just some random bullet point. It is literally topic number 1 for the unit. Why is that? Because everything else you're going to study, relations, functions, mathematical induction, even graph theory later down the line, is completely built upon the vocabulary of sets. I mean, you can't really understand how elements relate to one another if you don't first know how to group them together, right? Master this first step, and the rest of the course becomes significantly easier.
Section 2. Set fundamentals and types.
So what actually is a set? At its core, it's just a well-defined collection of distinct objects. But how do we actually write that down on paper? Well, we've got two main ways. The first is roster form, which is super simple and direct. You literally just list out every single element inside curly braces. Like A equals 2, 4, 6, 8, 10. Easy enough. But what if your set has a million elements? You don't want to write all that. That's where set builder form comes in. Instead of listing every element, you just define a rule. You'd say A is the set of all x, such that x is an even number between 0 and 10. It's the exact same data, just expressed as a logical condition.
We also categorize sets based on their properties. You've got your empty or null set with absolutely 0 elements, your finite and infinite sets, and the universal set, which basically holds everything we're currently talking about. But the most crucial one here is at the bottom, the power set. Think of the power set as the master list of all possible subsets of a given set, and that includes the empty set and the set itself. If your original set has n elements, your power set will always have 2 to the power of n elements. Definitely keep that formula locked in your memory, because it is a classic exam question for sure.
Section 3. Core set operations. All right, now for the fun part, manipulating these sets. First up is the union, symbolized by this big U shape. The union of sets A and B includes all elements that are in A or in B or in both. When you think of a union, I want you to immediately picture a Venn diagram with 2 overlapping circles. The union is everything shaded in, both entire circles. You're basically just tossing everything into one giant bucket, just making sure you don't accidentally list any duplicates. Let's test that out immediately. If set A is ABC and set B is CDE, what is their union? Go ahead and hit pause on this explainer right now, grab some scratch paper, and write down your answer. Okay, here's the solution. The union of A and B is A, B, C, D, E. Notice how C was in both sets, but we only wrote it down once. Also, check out the cardinality here, which is really just a fancy word for the number of elements inside the set. It's exactly 5. If you got that, you're perfectly on track.
Let's keep building that toolkit. Next up is the intersection, which is symbolized by an upside-down U. This time, we only want the elements that are common to both A and B. Going back to your mental Venn diagram, visualize just that middle, overlapping football-shaped region getting shaded in. That's the intersection. It's the shared ground.
Time for another exercise, and heads up, this one has a slight trick to it. If A is 2, 4, 6, 8, and B is 1, 3, 5, 7, what is the intersection? Pause the explainer and solve it. How did you do? The answer is actually the empty set, symbolized by that circle with a slash through it. Think about it. Set A is all even numbers, and set B is all odd numbers. Because they share absolutely 0 elements, their intersection is totally empty. When this happens, we call them disjoint sets.
Moving right along, we have set difference, written as A minus B. This is the set of elements that are in A but are not in B. Now listen closely, because unlike basic addition or multiplication, the order you write the sets here matters a ton. A minus B is absolutely not the same as B minus A. You're essentially taking the first set and deleting anything from it that also happens to appear in the second set.
Let's actually prove that order matters. Set A is A, B, C, D, and set B is C, D, E, F. I want you to find both A minus B and B minus A. Pause real quick and solve both.
Let's check your work. A minus B is just A, comma B. We started with set A and ripped out C and D because they were hiding over in set B. On the flip side, B minus A is E, F. We started with B and removed C and D because they were in A. Two totally different results, right?
Section 4. Laws and Cartesian products. Okay, this brings us to one of the most powerful and honestly coolest rules in discrete math, De Morgan's laws. The first law basically states that the complement of a union is perfectly equal to the intersection of their individual complements. I know, it sounds like a massive mouthful, but let's break it down using a universal set of 1 through 8. If set A is 1, 2, 3, 4, and set B is 3, 4, 5, 6, their union is 1 through 6. The complement, meaning everything outside that union, is just 7 and 8. Now, if we look at the right side of the equation, the complement of A is 5, 6, 7, 8, and the complement of B is 1, 2, 7, 8. What is the intersection of those two? It's exactly 7 and 8. See? The math works out perfectly, and this is a huge deal because it allows computer scientists to rewrite and heavily optimize complex Boolean logic in their code.
To wrap up this section, we have the Cartesian product, written as A cross B. Now, instead of giving you a flat list of elements, this spits out a set of ordered pairs. You pair every single element in set A with every single element in set B. So for example, if A is 1, 2 and B is AB, the product is 1A, 1B, 2A, 2B. This specific operation is the mathematical foundation for multidimensional arrays and tuples in programming. And again, massive warning here, order matters. A cross B does not equal B cross A.
Section 5. Mixed practice problems.
Before our final boss battle here, I wanted to give you a screenshot-worthy cheat sheet of all 6 operations. We've got union, intersection, difference, complement, Cartesian product, and one we haven't actually tested yet, symmetric difference, which is symbolized by that little delta triangle. Symmetric difference is the set of elements in exactly one of the sets, but not both. If you're a programmer, it's the exact equivalent of an exclusive OR. Go ahead and take a mental snapshot of these symbols. All right, here is your final exam challenge. We have a universal set of 1 through 10. A is 1 through 5, B is 4 through 7, C is 5 through 9. Your mission? Find the symmetric difference of A and B, and then find the intersection of that result with the complement of C. I know it looks a little scary, but don't panic. Just take it one piece at a time. Pause the explainer right now and give it your absolute best shot. Okay, let's dive into the solution and conquer this terrifying equation step by step. Step 1, the symmetric difference of A and B. What is in A or B, but definitely not both? That gives us 1, 2, 3, 6, and 7. Step 2, the complement of C. What is in our universal set of 1 to 10 that is not in C? That gives us 1, 2, 3, 4, and 10. And step 3, now we just find the intersection, the common ground between the result of step 1 and the result of step 2. The numbers they both share are simply 1, 2, and 3. And there is your final answer. See, even the most complex exam problems are really just simple operations stacked together.
Before we wrap up, I want to leave you with this golden rule directly from the course notes. Always draw the Venn diagram first when a problem feels confusing. It completely turns an abstract expression into a simple visual shading exercise. Whenever you get stuck on a test, just map it out visually. You've now mastered the foundational vocabulary of sets, but here is my final question for you. Now that you know exactly how to group data perfectly, how do you mathematically define the complex relations in functions between these different groups? Think about that as you get ready for the next chapter of your course. Thanks so much for hanging out with me on this explainer, and I'll catch you next time.